Hi friends, welcome to the fourth and final part of my overview of the pipelined MIPS risk processor. In this part I'm going to talk about branch prediction. This will be a simple introduction to branch prediction. I may in the future put together a discussion of more advanced branch prediction techniques. And this discussion, although continuing and finalizing the MIPS series, is also applicable to other risk processors and simple branch prediction approaches. So recall that one of the approaches to help reduce the impact of control hazards in the MIPS processor is to move the decode logic into the, to move the branch logic into the decode stage. So here we see the MIPS processor with a decode stage branches. And when we have the decode stage branches here, we add the forwarding logic in order to be able to forward, and we also make the hazard unit able to stall fetch and insert a bubble in the pipeline, and to be able to flush or squash the next instruction in case the branch is taken. When we flush the next instruction when the branch is taken, we basically jump to the branch target on the cycle after the next instruction or the bubble is pushed into the pipeline. When we have branch in the second stage of the pipeline, this means that whenever a branch is taken, we lose one cycle of performance essentially. Right? When the branch is taken, we have to flush one instruction. So that's going to increase the CPI for taken branches to 2. And for untaken branches, CPI will be 1. Although we can use delay slots to fill up that flushed space and then avoid having to squash the instruction after the branch, this requires the compiler to be able to find instructions that are safe to put into the branch delay slot. And when branch delay slots, or rather when the branch decision point is deeper in the pipeline than the second stage, it becomes increasingly harder for the compiler to find useful instructions to put there, and then it will put no-op instructions there, and you're always paying the price of the flushing even for non-taken branches. So to do better, we're going to look into branch prediction. So the idea behind branch prediction is to assume the outcome of the branch and proceed without waiting to see what the branch outcome is, and then check if you were right later. So the simplest approach is to predict not taken. Always predict branches will not be taken, continue to fetch and execute the sequential instructions, and when the branch is taken, then the pipeline stalls and you flush the instructions that you fetched. This is implicitly what we've already been doing in the MIPS pipeline by fetching the PC+4 and flushing it in case the branch is taken. So in this scheme, if the branch is taken, we flush the instructions that occur after the branch in the program. And therefore, they're in the pipeline after the branch. They're earlier in the pipeline. So when the branch decision is in the decode stage, then this causes a single cycle stall penalty or squash penalty for the taken branches. So like I said, this is automatically done in the MIPS pipeline. Also, what's automatically done in MIPS pipeline is that the branch, the instructions that get squashed have not changed the processor state yet, because all of the processor state updates happen in the mem stage and the write back stage, so the fourth and fifth stage of the pipeline. So you can squash instructions in the first 3 stages without having any side effects in the processor state. So when we have a misprediction under our prediction approach of static predict not taken, if we fetched the PC+4, the sub instruction, and it's in the fetch stage, and the branch is actually taken, and then we have to flush that instruction, and we know that we flush it by the end of the decode stage, and so that sub turns into a no-op in the pipeline, just like what we've been doing already. So the static prediction scheme is exactly what we've been doing. You resume fetching from the branch target address. So in this case, the branch target address is the PC+4 plus 2, 2 instructions. So 16, PC of 16 is where we find the next instruction, and we resume sequential fetching from there. Now, the thing about predict not taken is that this static prediction scheme works well when branches are at the top of a loop, because the branch condition is to leave the loop, and under the assumption that loops are more often repeated than not, the jump at the bottom of the loop going to return to the top of the loop will incur a jump stall overhead, and so you're still paying for that penalty. Now, some processors, including some MIPS processors, will use a delay slot after a jump instruction as well. Predict not taken really doesn't work well when there's a branch instruction at the bottom of a loop, which is a very common loop structure because it has fewer branches or jumps in general. And the reason for this is that you branch back to the beginning of the loop each loop iteration. So predicting not taken means that you're going to have to squash the fall through instruction every time that the loop iterates. An alternative would be to predict taken. So can we predict that branches will always be taken? This would always incur one stall cycle because we don't know the destination of the branch to take it to. If there's a way to determine the branch destination during the fetch stage, which we'll see that there is, then this scheme could be used. As the branch penalty increases because of a deeper pipeline, a simple static prediction scheme hurts performance because you have a bigger penalty every time you're wrong. Over time, as hardware became cheaper, we became possible to use more complicated branch prediction structures to dynamically predict branches at runtime using information accumulated at runtime. Predict taken still incurs a stall cycle until we figure out how to determine the branch destination during the fetch stage. So dynamic branch prediction uses a structure typically known as a branch prediction buffer or a branch history table, or BHT. This is a structure that stores history bits about branches in the instruction fetch stage. It's addressed by the low order, the least significant bits of the program counter, because that's the only information you have in the instruction fetch stage. And this table contains some bits that are passed into the instruction decode stage to tell whether the branch was taken the last time it was executed or not. The prediction bit may predict incorrectly. Past is not always prologue. It may be a wrong prediction for the branch in this iteration of a loop, for example. It may be from a different branch, which has the same least significant program counter bits. The reason the least significant bits of the program counter are used is that this will take advantage of the spatial locality of programs, which is that programs tend to execute close by in the program within a certain point of time. So you'll have fewer conflicts between instructions that are close to each other versus instructions that are farther apart. The conflicts in the branch history table lookup don't affect the correctness of the program, they just affect the performance because they may reduce the predictor performance, which is to say that you may not gain as much benefit from branch prediction as if the predictions were perfect. When the prediction is wrong, you still have to flush the incorrectly fetched instructions as before and restart the pipeline from the correct instruction, and now we'll update the prediction bits with the outcome of the branch each time that it executes. An example of a 4096 branch history table shows a variance of a 1% misprediction rate to 18% on some of the benchmarks from the SpecInt benchmark suite. So let's start with the simplest of branch prediction schemes, which is the one-bit predictor. One-bit predictor simply takes the last branch outcome and uses that to predict the current branch decision. So if the branch was not taken last time, then the branch history table will store a 0-bit for not taken, and the branch predictor will say, I predict not taken this time. Similarly, if the branch was taken last time, then the branch history table will store a 1 for that branch instruction, and the branch prediction will be taken. So let's take a look at a loop structure, and let's assume that the prediction for the branch at the bottom of this loop is 0 to start, which indicates that the branch is not taken. This is what you would expect it to be if this loop has executed one time through already, because the last time that the loop finishes, the branch is not taken. So the first time through the loop, the predictor will mispredict the branch because the branch is taken back to the top of the loop. This will invert the prediction bit, so the history is now a 1, so the prediction will be taken. So now each iteration through the loop, the prediction will be correct because the branch is taken back to the start of the loop, until the final iteration, at which the prediction is taken, but the prediction is wrong, and so the history is updated to a 0, which is why the history is a 0 when it starts. So as a simple example, if this loop iterates 10 times, we'll have an 80% prediction accuracy because the first and the last predictions are wrong, and the 8 iterations in the middle have correct iterations. So 8 correct out of 10 guesses is 80%. For a branch that's taken 90% of the time. So if we had just been able to statically predict taken, we would get a 90% accuracy. A 2-bit predictor scheme can give us a higher accuracy because a prediction has to be wrong multiple times before the prediction bit might be changed. So here's a state machine diagram of what's known as a saturating 2-bit counter predictor. So the state bits here are shown in brown. 0, 0, 0, 1, 1, 0, 1, 1. These are that's a 2-bit saturating counter. So 0, 0 is the state of not taken, and the prediction is predict not taken. And if it's not taken, then the predictor bits remain 0, 0. So the history, the branch history table actually stores these state bits of 0, 0. The next state over is predict not taken. This is sometimes called weakly not taken. And the idea here is that the state bits are 0, 1. And if the branch is not taken, then it will return back to the predict not taken state, the strongly predict not taken state. And if the branch is taken, then it will move up to the predict taken state, which is a weakly predicted taken. So from predict not taken, it has to go either to strongly not taken or to weakly taken. So the weakly taken state has state bits 1, 0, and the weak version of it will go to a strongly predicted taken state if the branch is taken and it was predicted taken. If you predict taken and the branch was not taken, then you go back into a weakly not taken state. And then finally we have the saturating 1, 1 bits, where we predict taken as long as it's taken, we just stay at state 1, 1. So let's take a look at what happens 10 times through this loop. We'll assume we start here in this predict taken, which is what happens under the assumption that this loop is the only loop that's executing. The only branches that's executing is in this loop, and it's already gone through once. So we predict taken, and it actually is taken, so we're right on the first iteration. We're going to predict taken for all the rest of the iterations, and so we're right 8 more times, actually, so we're right a total of 9 times. And then on the fallout of the branch, we're wrong because we predict taken at the end. The branch is actually not taken. We return back to this predict taken, weakly predict taken state for the next time the loop runs. And so this gives us an accuracy of 90%. We're right the first time, and we're right each of the interior iterations of the loop, but we're wrong at the end of the loop. A problem with this 2-bit saturating counter predictor is that alternating branches cause problems. So suppose this loop structure only iterates 1 time. Not a terribly useful loop, perhaps, but it shows an interesting problem. We're going to assume now that we start out in this weakly not taken state, because that's where we'll start out in general based on this loop, this 1 time through loop structure. So on the first iteration, it's going to be incorrect. We predict not taken, but the branch is actually taken. And so we go up to the predict taken state. Now on the next time through the loop, this is the end of the loop, and we fall through and we're wrong on the loop fallout because the branch is not taken, and so we return back to the predict not taken state. And this means that our 2-bit predictor has an accuracy of 0%. So this is not great. A solution, simple solution to this is what's called a 2-bit predictor with hysteresis. So the idea here is not to use that saturating counter flow, but instead to skip from weakly not taken to strongly taken, or from weakly taken to strongly not taken. So you no longer transition from one weak state to another weak state. So the idea here is that we'll be in this predict taken state after the loop executed. When the loop is the branch is taken the first time, so we're right on the first prediction, we'll predict taken again, and it's not taken, so we'll be wrong on the fallout. So we still only have a 50% accuracy, but it's somewhat better. This kind of loop structure or branch structure motivates more advanced branch prediction schemes, which we may talk about at a later date. So the final problem to solve is how do we actually predict taken and fetch the predicted taken target in the fetch stage. So the branch history table predicts when the branch is taken, but it doesn't tell us where to take it. A different structure called the branch target buffer, BTB, in the instruction fetch stage is used to solve this. The BTB caches the branch target address. Sometimes this structure is also called a branch target address cache because it's a cache of the branch targets. It is also indexed by the least significant bits of the program counter. And if there's a hit, then the target is in the cache and the branch is taken, then we'll fetch the target. When the branch is first encountered, we don't know where to take the branch and we can't predict taken. So we always predict not taken the first time we encounter a branch, and we update the BTB with the branch target. On a predicted not taken branch, we ignore the value out of the BTB because we're not going to take it. We just use the instruction from PC+4. So the branch target buffer supplies the predicted target address. We need to fetch the predicted target address and the next PC+4 instruction in order to feed the decode stage. So the prediction bit in the IFID can select which next instruction to load into the IFID. But in order to do that, we would need to add another read port to our instruction memory so that we can fetch both the branch target and the PC+4 instructions simultaneously. A different approach is to cache the instructions themselves in the BTB. Since the BTB has to store a 32-bit instruction address, you could instead store a 32-bit instruction itself. So this is known as branch target folding. You put the instruction inside the branch target buffer. If the prediction is correct, then we can avoid stalls no matter what because we can feed the predicted instruction at the branch target into the IFID stage, or we can feed the instruction at PC+4 into the IFID stage. There is one subtle problem, which is that the BTB, being a cache, can have collisions. And so you may have the wrong instruction cached in the BTB. To solve this problem, there's some tags that are used in the BTB with the program counter, and also the PC target, the branch target rather, can be compared after the branch decision is already determined. So the branch decision in the decode stage is done in parallel with the branch target calculation. And so you can compare the output of the branch target calculation with the predicted branch target that you got from the fetch stage. And if they don't match, then you have to flush the mispredicted branch target and resume fetching from the correct branch target. So branch prediction is an effective way to resolve control hazards. You predict the outcome, you predict the target, and then you flush if either the prediction or the target was incorrect. Well, if you predicted a branch is taken, but you take it to the wrongly predicted address, then you have to flush that. You can apply the same notions to jumps, so unconditional jumps, and to procedure calls. You can predict their targets. These are much more predictable since you don't need to keep track of their history as long as you know that they are jump instructions and that they're always taken. So sometimes you'll use a separate table, kind of like a BTB only, because the history is not relevant. All you really care about is that it is a jump. You can apply the same notion to procedure returns. This is a little bit trickier because a procedure doesn't always return to the same address because it's not always called from the same location in the program. Different locations in the program can call the same procedure. So instead, what you can do is use a stack data structure to predict the return address, and you can pull that predicted return address off of that prediction stack. So hopefully later on we'll discuss more advanced branch predictions. I hope this was a useful overview of dynamic branch prediction for you.